Hey Pre-Calc, Mr. Rashid here, and today we're looking at how to find the sum of an infinite series, if it exists. Now normally you'd think, hey, infinite numbers, you just keep adding up the numbers to infinity. Well, am I just going to get infinity here? And so it turns out in some very special cases you actually get a finite sum, which is fascinating. So we'll see today how that works out. But before we get to that, let's look at some formulas for the arithmetic series, the sum of an arithmetic series and the sum of a geometric series. So we've seen these before, and these are all partial sums because we're ending at a specific n value. So we could also write this as S sub n here. So the first one is for an arithmetic series, and what we're doing is we're taking the first value of the series and the last value of the series and finding their average and then multiplying by n. Now this is a type of formula that we would use when we have the first term and the last term and we know the number of terms here. And so that's the first formula. Then the second formula we also have available to us, and we can use that to find the sum of an arithmetic series. And this is the one we use when we know the first term, but we don't know the last term. We also have the number of terms here. So those are the two. And then for geometric series, we have this formula. And I can also write this as a sub 1 over 1 minus r, and then keep this 1 minus r to the n over here to the side. So that's the way you'll see me writing it today when we're going through these infinite series. Okay, so let's start first with an investigation. So we're going to take a look at some series and find, well, what could be the sum of these series as the number of terms gets larger and larger. Okay, so the first one is 10 plus 5 plus 2.5 plus etc. Now, is this a geometric series or arithmetic series or something else? So let's find out. So if I subtract 5 here, then if I subtract 5 again, that next term should be 0, but it's not. So it's not an arithmetic series. But if I was to multiply here by 1/2 and multiply again by 1/2, then I'm getting here a geometric series. So this is geometric. And what I was doing was I was multiplying by 1/2, so that is my common ratio. And then I'm going to need to find the sum here today. So the sum formula also has a value a sub 1, which is the first term. The first term in this series is 10. Okay, so that's all I would need to know. And then I would also need to know the number of terms. So here it says find the sum of the first 5 terms. So let's write out the formula for this. So here, the first 5 terms means that n is equal to 5. So this would be 10 times 1 minus, and 1/2 is the same as 0.5, so I could say 0.5 to the 5th power, and then this is all divided by 1 minus 0.5. And if I do the math and all that, then this is equal to 19.375. Okay, so that's the first 5 terms. So now let's do the next 10 terms. So or the sum of the first 10 terms. So this would be 10, 1 minus 0.5 to the 10, and then divided by 1 minus 0.5. So the only thing that changed here from that first one is this, I'm raising that to the 10th power now. And so this is equal to 19.980. And then I'm going to skip writing the formula for these. Just if you were to actually calculate this now, the sum of the first 20 terms would be 19.999998. And then for the first 25 terms, we get 19.999 and another 3 nines. Okay, so for the first 25 terms, it's that. So let's think about this. What's happening as the number of terms is getting larger? Well, in this case, this sum of this series is actually approaching 20. This is approaching 20 as we get larger and larger number of terms that we're adding up. Okay, so that's our first investigation. And one of the things we're going to do after these investigations is think about what is the pattern? What can we come up with that's the pattern for this? All right, so the next one is an arithmetic series. So I can put here arithmetic. And I'm adding 4 every single time here. So adding 4. So the formula for the sum of these has an a sub 1, which is the first term here, which is equal to 3, and then a d value, which is the common difference for arithmetic series or sequences, and that is positive 4. Okay, so let's find now the sum here. And with this one, we're going to use the arithmetic formula. So, or maybe for the first 5 terms, I can skip that and just write, okay, 3 plus 7 plus 11. And then if I add 4, that's 15. If I add 4, that's 19. If I plug that all into a calculator, that is 55. Okay, so the sum of the first 5 terms, this arithmetic series, is 55. Then for the first 10 terms, now we have to use our formula. So we don't have our ending term, so this is going to be 10 terms, n is equal to 10, divided by 2. Then I've got 2 times a sub 1. A sub 1 is 3, as I've written up here. And then we need our n, which is 10 minus 1 times the d value, which is 4. Okay, so this is all in parentheses, or let's put it in a bracket there. And so this 10 divided by 2 is 5, and then everything in that bracketed stuff is 42. So this turns out to be 210. Okay, and then if you keep going for the first 50 terms, you'll see that the sum is 5,050. If we use that formula, and then the only thing we would change with the 50 is the n value. So this 10 would change to a 50, and that 10 would change to a 50. Otherwise, it's the same thing. Then if you did the first 100 terms, you'd get this number, 20,100, as the sum. So you'll see for these arithmetic series here that as your number of terms get larger and larger, the series actually gets larger and larger as well. The sum gets larger and larger. And so this actually tends towards infinity. And we can also just say that this means the sum does not exist. And we can write that in shorthand form as D and E, does not exist. And give me problems that don't exist all day. I can write does not exist very easily. We don't have to actually find any of these sums, as we'll see, if it does not exist. So The other term that's often used to describe these kinds of series is that they're divergent series. And that comes from the fact that just the series gets away from you. You can't really put a handle on what the actual sum is. Let's call that divergent series. The other one that we saw where it actually tended towards a specific number, so these are called convergent series. So this is a convergent series. Okay, so before we get into that, let's look at another example here. So in this example, I'm going to have a geometric series, and I'm going to just start with 8 and start doubling these. So 8 plus 16, 32, 64, 128, and I'll just keep going. So what I'm doing here is I'm multiplying by 2 to get the next term in the series here. Each element in this sequence is multiplying by 2, so my R value is equal to 2. Now, if I was to keep adding, right, these terms are going to get larger and larger here. So this is a geometric series. And if I was to use my sum formula here, so a sub 1 over 1 minus r times 1 minus r to the n, and let's plug in some values here. So a sub 1 in this case is equal to 8. That's my very first term there. And r is equal to 2. I'm just multiplying by 2 every single time. And let's leave the n. Let's think about what the n is as we get larger and larger. So this is a sub 1 is 8 divided by 1 minus 2. And over here I've got 1 minus 2 to the n. Now if n was 10, this would be 2 to the 10th power. If n was 20, 2 to the 20th power, right? You'll notice that this part here doesn't, 8 divided by 1 minus 2, 1 minus 2 is negative 1, 8 divided by negative 1 is negative 8. So I get negative 8 times 1 minus 2 to the n. And this part here, I'll just get a very, very large negative number. So a large negative number times negative 8 will give me an even larger positive number. Negative times negative is positive. So as this thing gets larger and larger, this whole thing will tend towards infinity. Well, this part in the parentheses will tend towards negative infinity, but then times the negative, I tend towards positive infinity. So that's the third example we're using, and this is a geometric series. So what's going on here? We've got geometric series that converges to a number. We've got a geometric series that diverges, right, goes off to infinity, and we've got arithmetic series that where it diverges as well. It goes off to infinity also. So what is the general pattern here? So it turns out that for arithmetic series, if they're infinite, then those infinite arithmetic series actually are all going to be divergent, because no matter what you keep adding, if I keep adding, right, I'm going to tend, as I go to infinity, I'm just going to tend to infinity, and the series sum is not going to exist. And likewise, if I keep subtracting negative numbers, if I keep subtracting, so this is going to tend towards negative infinity, and also that does not exist. Right? So for arithmetic series, they're all going to be divergent, and the limit as you increase the amount of terms in that series is not going to exist. Okay, so we've seen now that for arithmetic series, they're divergent. They're going to go to infinity or negative infinity depending on what kind of series there is. So what happens to geometric? So let's look at geometric here next. So we're going to look at infinite geometric series. Okay, and with infinite geometric series, there's actually three different possibilities here. So one of them we actually saw here. We had the series 8, 16, 32. So in this geometric series, we had an R value that was bigger than 1. So let me write out this sum here. So if the R value was bigger than 1, then what happened to our formula, we had our a sub 1 over 1 minus r, that part was fine, but then 1 minus r to the n. So when our r value was bigger than 1, what happened is as we raised this to larger and larger powers, that number just got larger and larger, and so the series actually went to infinity. So the limit here did not exist. And it turns out that if you've got a negative r that's larger than 1, then it's going to do the same thing. So negative r going to larger and larger numbers there, that is also, it depends on which n value you're using, but it's going to tend towards negative or positive infinity. So another way to write this is to say, well, the absolute value of r greater than 1, then the limit here for that sum is not going to exist. Okay, so now for infinite geometric series, you can also have r values that are less than 1. So the r values here could be less than 1, and we saw an example of that in one of our cases here. Right? We saw an r value of 0.5 or 1/2 here. So in the case where the r value is less than 1, or the r value is greater than negative 1, so it could be negative 0.5, in those cases we have this sum formula, 1 minus r to the n. And what happens when r is less than 1 is if we raise that to larger and larger powers, right? So if I've got 0.5 to the 1, that's 0.5. If I got 0.5 to the 2, that's 0.25. And you'll notice that these larger powers, if this number is less than 1, tend towards 0 here. Right? So if on my calculator here, I'm going to put 0.5 raised to the 20th power, I get a really, really small number, like 0.0000953, something like that. So if I'm raising this 0.5 to infinity, right? So instead of this n here, I'm going to replace that with infinity. Then if that r is less than 1, what happens is this whole thing goes to 0. It just becomes smaller and smaller. And so I'm left with a sub 1 times 1 minus r times 1 minus 0 is just 1. I don't need to write that 1 there either. So my series, my infinite series is going to converge to this value here, a sub 1 divided by 1 minus r. This whole thing, 1 minus 0 becomes 1, and then 1 times this is just 1, or whatever this is, a sub 1 over 1 minus r. So another way also to write this is that the absolute value of r is less than 1. So these are just different ways of writing the same thing. If your r is between -1 and 1, or if your absolute value of r is less than 1, then your series actually converges, right? So it converges, so it's a convergent series, and it tends towards this limit. Okay, so that's what this slide is about here. So it says that the formula for an infinite geometric series is this right here, and I showed you where that came from, and then also this is where it applies. Right, so a lot of students, they just see geometric and they start using this formula. Be very careful. If it's an infinite series, then this formula only applies for the case where r is between -1 and 1. If you use it when the r is not between those values, you're just getting some nonsense numbers. Okay, so let's do some examples now. So find the sum of some series here. So 4 plus 8 plus 16. So this looks like a geometric. So multiplying by 2, it looks like every time. Right, so it's geometric. My r value is equal to 2. And these three dots here indicate that it's an infinite series, right? So it's going to go on forever. So r is not between -1 and 1. R is not between -1 and 1. So these are relatively straightforward. You just write does not exist for the sum for that. Right? It tends towards, it's just going to get larger and larger towards infinity. So the sum does not exist. So for geometric series, the main thing you're looking for is that r between -1 and 1. So I can write that up here. This is the main thing we're looking for geometric. Right? Is it geometric, then is your r between -1 and 1. Okay, so let's do the next one here. So going from here to here, this looks like it's geometric also, and I'm dividing by 3 every time, or multiplying here by 1/3, multiplying here again by 1/3. So my r is equal to 1/3. So remember what I said here before, it's geometric and my r value is less than 1, greater than -1, so it's between 1 and -1. So I'm all set. I can actually use my formula now, which is s is equal to a sub 1 divided by 1 minus r. So in this case, I can write my a sub 1 value here is the first term. My first term is 27, and then 1 minus 1/3, which is 2/3. So 27 divided by 2/3 is 40.5. So that is my sum. So yeah, that's really fascinating, amazing. And first time I saw this, I was really surprised. Like, if we keep adding an infinite number of terms, then it's going to go towards 40.5 for that. Okay, so let's do a couple more here. So this is, let's see, is this geometric? Doesn't look like it. So plus 9, plus 9. So this looks like an arithmetic series, and so and this indicates that it's going to go up to infinity, the infinite number of terms here. So remember what we said, arithmetic series, the limit or the sum does not exist. Right? It's going to just get larger and larger and larger. Okay, and then the very last one here, so we've got 10 minus 4 plus 1.6, so my r value, it looks like, I can use the successive terms here. -4 divided by 10 is -0.4, so my r value is -0.4, and so that is in between, my r is in between -1 and 1. -0.4 is greater than -1, right? And the other thing to think about is just some students, they see a fraction and they think it's going to converge. No, you got to check that fraction out and see, does it actually, is that fraction between these numbers here? Is it less than 1? Is it greater than -1? So let's finish this one off. We have s is equal to my starting value is 10 divided by 1 minus, in this case, -0.4. So that's going to be 10 over 1.4 because a negative changes to positive. So I add those, and this is equal to 7.143 is what I get on my calculator. Okay, so let's finish off here with some additional examples. Now, you'll notice what's different about these problems is they're all written in sigma notation. Right, so we'll see how to deal with this if it's in sigma notation. So we know that arithmetic series are going to diverge. The limit or the sum of those infinite series is going to not exist, right? So the key is to identify, is it geometric and is the R value between -1 and 1? So from this sigma notation, you kind of look for the whole thing to be written as some kind of a sub 1 times r to the n minus 1. And even if it isn't like that, you'll generally have something in parentheses like this raised to a power. So as soon as you see that, you know that is your r value. So my r value in this case is 3/4. Even it doesn't have an n minus 1, like check out this second example. It's got a 2 raised to the n power, so my r in that case is equal to 2. So that's a quick way to see what is your r value for geometric sequences, as long as it's in that kind of base raised to an exponent. Your r is raised to the exponent. Then the other thing is, so the formula is for an infinite geometric series. The formula is a sub 1 over 1 minus r. Now your a sub 1 is your starting term. That's going to be your first term. And so if you've got something in a sub 1 to the r minus 1 and n equals 1, and sometimes your indexes just may be in starting at a weird spot. So the key thing is when you're using this formula for infinite series, now we can tell these are infinite series. They've got infinity symbol at the top here, so there's no end. It just goes on forever. To find that starting value, plug in your first number. So it says here I'm going to start at 1. So if I plug in 1 there, I get 3, then 3/4 to the 1 minus 1. That 1 minus 1 is 0, and then anything raised to the 0 power is 1. So this is just equaling 3. So my starting value here is equal to 3 in this first example. So let's replace some of this here. So this is equal to 3 divided by 1 minus 3/4, and that is equal to 12. Now, of course, you're going to need to check, is your r value in between -1 and 1? So in this case, my r value is between 1 and -1. So let's replace that also. So I'm going to replace this. I know that 3/4 is less than 1, and it's definitely greater than -1. So I'm all set. I can use this formula and find the sum of that infinite series. Now, what about this case here? We have 2, and 2 is not in between. This does not work at all. 2 is definitely greater than 1, and remember what I said before, that 2 to some power, that's just going to be bigger and bigger numbers, and so we just write does not exist for this problem here. Okay, and then the very last one, this is not geometric. that doesn't automatically mean that it does not exist, but if you look at the general pattern here, we're going to have 1 squared plus 1 is 2, then 2 squared is 4 plus 1 is 5, and these are sums actually, so let's write that properly. So this is 2 plus 5, 3 squared, 9 plus 1 is 10. And you'll see, notice that the numbers just keep getting larger and larger. So as this thing goes towards infinity here, the limit does not exist. It's going to be larger and larger, and it's going to be a divergent series there. Okay, and then you might see some examples on your homework that look like this. So let's do one more example here. N equals 1, and maybe you have something like this, 3n minus 4. And so that is an arithmetic series because it's got this y equals mx plus b, or you've got that kind of linear format there. If you don't recognize it, that's fine. Just write out a few terms and you'll see that it's just arithmetic. It's just going larger and larger, and so the limit here does not exist. So that is the final example, and we are done. I'll see you in the next video. Bye.